Hi, and welcome to a video on infinite series. This should be our first video on the transition from a sequence, which was just that listing of numbers. So for example, 1, comma 2, comma 3, comma 4, dot, dot, dot. Now to an infinite sum. So where you're taking that same list or sequence that you had of numbers or terms, but now instead of just putting a comma in between, we're going to look at what is this sum. And so we put this sigma notation in front, and that sigma notation from Calc 1 should have been learned when you talked about Riemann sum. So we are adding them all up from 1, so that's your starting value, whatever is underneath your sigma, and we're ending at infinity, which is our final value for that term that we're stopping at in this case, which making it an infinite sum. Now this image that I've provided for you here over to the right is a really special snowflake. You can actually look it up if you want to, and it's the Cook snowflake. And what happens is if you start with an equilateral triangle and you break up that triangle, each step of the process, that middle third is going to be broken up. So this middle third right here, and I put a new equilateral triangle pointing out on that middle third. And that is constructed from an infinite number of non-overlapping equilateral triangles. You'll notice they never overlap as you go through. So we can express its area as a sum of infinitely many terms. So that gets us started with if we can actually find the area of this snowflake. All right, so one important thing to note is that you do not always have to start your series at n equals 1. We talked about that when we talked about sequences, although many of our sequences did default to starting at n equals 1. We have reasons for our series to start maybe at n equals 2 or n equals 3, or to back it up perhaps and start at n equals 0. So something finite to start with, I can find a partial sum of the series. So while it might be impossible to add up all the terms, right, from 1 to infinity, for example, I can find a partial sum, which again is this idea that it's going to be some finite value. And so that's what we did here. So we took this list or sequence and turned it into a sum. So that's why it doesn't say a sub n or a sub k. This is s sub k now. So I have this infinite sum. So this is my series. And then right after it, I did write it in summation notation. So we can see that this is the pattern, if you will, from the sequence section that you had to write, but I'm summing up all of those terms. So I can also just add up the first two terms. That's the sum of s sub 2. S sub 3 would be s sub 1 plus s sub 2 plus s sub 3, right? The sum of the first 3 terms, sum of the first 4 terms, sum of the first 5 terms, etc. So here I am at the sum of the first 5 terms. Now, if you graph that, what you'll notice is that, so this is, for example, at n is 5. So you're looking at what is the sum of the first 5 terms. Well, what I hope that you notice is that does appear to be leveling off. While it appears to be increasing for my sum, it is concave down, so I'm not necessarily increasing at an increasing rate. I'm increasing at what we would say a decreasing rate. So I'm concave down here. So it does appear to maybe be leveling off or approaching some value, and that sum seems to be approaching 2. So we can talk about, what does that mean? So let's start doing that by looking at geometric series, and I think these are pretty basic that everyone kind of starts with talking about a geometric series. And what I want to start with isn't necessarily what's in the box, although I'll go over what's in the box on the next page, but there are different ways to write the same series using summation notation. So if you'll notice, my base of 1/2 stays the same every time. And what I also want you to notice is when I wrote out the series, I got the same series each time. Now what changes is your starting value for n. So in this first one, we're going to start at n equals 1. So this first term right here is 1/2 to the 0, which is 1. And I continue on. In this middle series here, my starting n is 0. But what you'll notice is it's not to the n minus 1 anymore. Now it's just to the n. So this first term is 1/2 to the n. Well, n starts at 0. So 1/2 to the 0, which is 1. Now, like I said, we don't have to start at 0 or 1. This last interpretation, or the way they wrote it here, starts at n equals 5. Okay, fine, but my first term is still this 1/2, and then n minus 5. 5 minus 5 is 0. And so my first term is still 1. So there are many ways to write the same series. So please, please keep an eye on what is your starting n value, because that could change and we could assume or make assumptions that it's 1 when it might not be. So this box is also written basically on this page just to kind of help us out here. And what we're going to look at is first in this geometric series, right? A geometric series must have a common ratio. So we're going to have to find out what that ratio is. Now, if the absolute value of the ratio is less than 1, we will converge. So another way of writing that is just if it's between -1 and 1, logically. Or if that absolute value of that rate is greater than 1, then the series diverges. And I will use these 3 dots often, and it means therefore. And I didn't make that up. That's just something that mathematicians use specifically in proofs often. So we'll use that throughout this chapter here. Now, if I can say that the series converges, if I think I can find a finite sum that this series will be approaching, just like 2 on the graph that we looked at, then I can say what the geometric series sum will be. Geometric series is unique in this. There are only 2 types of series that we will talk about that we can find their sums, and that is telescoping and geometric. And we'll talk about both of those in this section. Others, we just know that it converges and we can get close. We can get within a desired level of accuracy. We'll talk about that error throughout the chapter as well. How close are you to a good approximation of that sum? But we can't necessarily get exact unless we are geometric or telescoping, and I'll show you that one probably in video 2. So here's our examples. We're going to determine whether the series is convergent or divergent, and then if it converges, we're going to find its sum. So I wrote these, you'll notice, kind of in 3 different ways. 2 of which are summation notation using the sigma, but 1 of which the terms are written out. I think it's more clear if the terms are written out, so even if they were not, I would go ahead and do so. But I might also need to see a rewrite to see what my common ratio is. I don't know, that's entirely up to you. So this would be 10 minus 2 plus, this is 4/10, which is 2/5. This is 8/100, or 2/25, plus dot, dot, dot. I really think that even though you don't love working with fractions, they are easier to work with in this case than the decimals. So now I can say, is this series geometric? Well, it's a geometric series if I can come up with what is the common rate or ratio that I am multiplying by each time. I can see I'm dividing, but we don't want to talk about that. We want to talk about what are we multiplying by each time. So I'm multiplying by a negative because I'm going from positive 10 to negative 2. So I'm multiplying by a negative 1/5. Does that work again to get me from the second term to the third? Yes, because the negative times the negative would be positive, and that would turn it into 2/5. Does it work again to get from positive 2/5 to negative 2/25? And yes, I can say without a doubt, my common ratio is negative 1/5. So I just checked to myself, yep, this is a geometric series. The common ratio being negative 1/5, which means my absolute value of that is less than 1. So I would say this will converge, which means I can find the sum, again, only because it's geometric. So if it's geometric, we can go to finding the sum. And here's why it's helpful to have that first term written out. If it converges, then we can find the sum. And so we're going to take the first term, right? So this is going on the formula here. The sum is the first term over 1 minus that common ratio. So that's why I like having all of my terms written out. My first term is 10 over 1 minus the common ratio, which is negative 1/5. Personally, I like to just multiply by whatever that common denominator is to get rid of my complex fraction here. So my numerator will become 50. Distribute that in. So 5 plus 1. And so that would be 6. So if I have 50 over 6, that means that the sum is approximately, or equal to, I guess I should say, 25/3. Okay? So let's do it again. Well, if I have it written with the sigma notation, I strongly would encourage you to determine, first of all, if it's geometric or not. We're going to a place where we're going to have a whole bunch of different kinds of series, and you're going to have to determine what kind of series it is. And so I think it's really important that you have some of these terms written out. I like to have 3 or 4 at least, because you can't tell with just 2 terms what it is. So this will be 3 times 1/5. And if n is 1, I'm starting with 1/5 squared, plus 3 times, this will now be 1/5. And if n is 2, that'll be cubed. And I can probably see the pattern pretty quickly, but even if not, I at least find 3 terms. Okay, so I can see that in my common ratio, I can see, first of all, yep, this is what I would consider to be a geometric series. So I'll write geometric series, and I'm just going to check that because, yep, I have identified I have a common ratio that gets me from term to term forever, but the common ratio does not have a 3 in it. That 3 is just a constant coefficient out there. What I'm really multiplying by each time is 1/5. And that ratio is less than 1. And so I would say, therefore, those 3 dots in a triangle converges. Again, it's all based on that common ratio. Now, this should make sense to you because if we remember something like y equals ab to the x, so if I'm looking at this y equals ab to the x, that was our typical exponential growth or decay. And what I remembered is if that base was less than 1, we had exponential decay. So it looks something like so. And so my last term would end up looking like 0, which at least gives me a chance for something to converge. We'll talk about something called a divergence test later, because if my series is growing, if I'm looking at the series of 1 plus 2 plus 3 plus 4, that does not have a chance of having a convergent sum because I'm going to be adding on so much at the end. My sum is going to continue to grow if I graph my sum. So this should kind of make sense to you why it needs to be less than 1 if it's geometric. Okay, now because it converges, I can go ahead and find the sum. And again, my sum is going to be the first term, which I should know is 1 over 5 quantity squared times that 3. So there's my first term, over 1 minus that rate that I found earlier. In this case, it was positive 1/5, so it just would be 1 minus 1/5. And if you rewrite this, this is 3 over 25 all over 1 minus a fifth is 4/5 if you wanted to do that. You can multiply by 25 over 25. You can multiply by the reciprocal. It doesn't matter. However you learned your complex fractions, so that you can do. So my sum is going to be 3 over, that would leave a 5/20. So it's a pretty small sum here. Okay. Now another thing that you can check on your calculator is you can add up a whole bunch of these terms and you can see if your sum is getting closer and closer to 3/20 the more terms you add on, and it should be getting there. All right, let's do it again. If you think you're pretty good and solid with geometric series, you may want to pause the video and see where you get. I'm going to start by writing out the first few terms of the series and seeing what my common ratio is if in fact it's geometric. So my numerator is always a 5 regardless of n. And so when n is 1, I have 3 to the 0, which is positive 1. And I do tend to write my terms as fractions if I think there's going to be fractions later on. And if you need to keep track, that was n equals 1. So sometimes people put these below the term that they're adding just so that they can see what n they're on. So 5 is in my numerator. If n is 2, I have 3 to the 1, or just 3. And then plus 5 is in my numerator. If n equals 3, I have 3 squared. And it's okay to leave powers. My next one, if I wanted to just be sure, 5 would be in the numerator. 3 to the 4 minus 1 would be 3 plus dot, dot, dot. Don't forget that plus dot, 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 because otherwise you're going to think there's only 4 terms here, and there's not. There's an infinite amount of terms, right? If you look, remember, we have an infinite sum. Okay, so do I think this is geometric? So I'm kind of asking myself that question as I'm writing this down. So if it's geometric, I would have a common ratio from term to term. So yep, I'm multiplying by 1 in the numerator and 3 in the denominator, and that trend seems to continue on forever. So yep, it's a geometric series. My common ratio is 1/3. That ratio in absolute value form is less than 1. Therefore, this series will converge. And because this series converges, I can find its sum. And the sum will be first term over 1 minus the rate. So that's why it's so important that you identify what that common ratio is. So 5 over 2/3, or you can write this as 15 over 2. If you multiply by 3 over 3, you'll get there. Okay, so I did another one just so you could see what this looks like if it does not converge. So if I write out the terms pi over 2 plus pi squared over 4 plus pi cubed over 8 plus dot, 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 so I've got this infinite series idea here. This is geometric. When you look from term to term, you're multiplying by pi in the numerator each time, and you're multiplying by 2 in the denominator each time, so your common ratio here is pi over 2. So that works great, it's geometric. And then what people forget to actually calculate is pi over 2 is greater than 1. So this is looking like exponential growth. So each next term is going to be much bigger than the previous one. So it's growing. So the sum is going to be growing at such a high rate. So I'm not going to be able to find or estimate or anything that infinite sum. And so we just simply say because that rate is greater than 1, this series diverges. And you're not finding a sum when it diverges because you can't. And then this should make a little bit of sense to you that if we have addition in our series or in our pattern that we wrote for how to get each term, it cannot be geometric. Remember, geometric is that you take a term and you multiply by some common ratio to each term to get the next one. So we can't be adding something on because then it's not going to be geometric anymore. So that should signify something to you now that, okay, wait a minute, I want to look at this as two separate series and I want to add them together. So if either one of these series don't converge, if either one of these series diverges, I can't find a sum. So I'm going to try to find a sum of each series separately. So what I did was take 2 over 5 to the n and then add that to the series of 3 to the n over 5 to the n. And so I split it up. So it's basically like doing two problems in one. Then I would write out the series, figure out that common ratio. It was less than 1, so it converges. So I found the sum. And start all over again with the second series, right? Write out the series, find your common ratio. It's less than 1, so I know it converges. So go ahead and find the sum, and then define the total sum of both of your series, add them together. So I hope it makes sense of why if you have some addition in there, it might not be geometric. So if you write out some terms and it's not appearing geometric, maybe you need to split that up into two different series. Okay, something that you may have done early on in your math career, and when I say that, I mean like grade school. You may have taken this 2.4646464646, and you may have been told somewhere along the way how to turn that into either a mixed number or an improper fraction. But it's actually an infinite series. So I'm going to write it out first in decimals, then we'll do it in the fractions because I think that'll help a lot. So first of all, this is 2 plus, because the whole 2 just has to kind of come along for the ride for a little bit. That is not the infinite part. This is definitely the infinite part, right? And it's, of course, 0.46. I put the bracket right over that. So what this actually looks like if I write it out with decimals is 0.46 plus, well, I've already got these first two accounted for. So now if I add something to it, I don't want to change those first two decimals. Okay, so if I add 0.46, that's the tenths and the hundredths. So I want to make sure now I don't change the tenths in the hundredths. So I'm going to add 0.0046, because again, that's going to leave the first two digits alone there after my decimal point and only change the third and fourth. And then it would be plus 0.000046, and then it would be plus 0.00000046 plus dot dot dot. And so if you write these as fractions, you might see it even a little bit better. This is 46 hundredths, which I can write as 46 hundredths or 46 over 10 squared. I would not recommend, some people want to simplify that immediately, but everything is going to be 46, so I'm going to leave that alone. Plus, the next one is going to be 46 over 10 to the fourth. Plus, the next one here is going to be 46 over 10 to the sixth, and that pattern will continue on forever. And so what I see is that this part of it is geometric. So this is a geometric series. Yep. Where my common ratio is 1 over 10 squared, or 1 over 100, which that common ratio is definitely less than 1. So I'll say therefore converges. And if it converges, we can find the sum. And I'm not going to be able to write this as a ratio of integers unless I can find that sum of all of those decimals. So here we go. The sum will be, and don't let me forget to add 2 onto this in the end here. So our sum will be the first term, which was that 0.46, or 46 over 10 squared, over 1 minus the common ratio, 1 minus 1 over 10 squared. And then again, I just like to multiply by 10 squared, which is 100 over 100. And so this will become 46 over 100, right, minus 1. So 46 over 99. So some people might have memorized or just told you however many numbers are in your repeating part of your decimal, then you have that many nines. So if I have 4, 6, I have 2 digits that are repeating every time, 4, 6, 4, 6, 4, 6, then it'll be over 99. Well, this is in fact why. It's because of how many decimal places. And so it's because of this geometric series, truly. So my overall number that I'm trying to write here is 2 and 46/99. And if I write that as a ratio of integers like it wants me to, 2 times 99 is 198. So 198 plus 46 would be 244 over 99. And if I check that, I can certainly drag in like a graphing calculator here, and I can say, okay, well, I've got 244 divided by 99. I want to make sure I just did my computation in my head correctly. Yep, and there it is. And it's just, rounding that very last decimal for us, whether we think that's helpful or not. Okay, so that's how you can turn a number into that ratio of integers. All right, last one here that we're going to do from scratch, and I want us to see what this is going to look like. So really, in essence, we're going to kind of start from scratch here because that's only part of it. If I write this out, okay, in the expanded form, not just in this summation notation here, I'm starting at n equals 1. This is an alternating series because of that -1 to the n, so each term is going to be alternating signs from the previous. But I'm starting with it being odd, so I have negative and I have the quantity x plus 1 to the first. Then I will have plus, because it will be -1 squared, right, when n is 2, which the quantity -1 squared would be +1, so that turns it plus. And then I have x plus 1 squared minus the quantity x plus 1 cubed plus ... Okay, so that's what my series will look like when I write it out, this of course being n equals 3. So is this series geometric? Yep, it sure is. And so let's figure out what that common ratio is each time, and then we'll read the question and see what we're asked to do here. So what is my common ratio? Well, I'm multiplying by a negative every time because that's how it alternates terms, so that negative has to be there. And then your quantity x plus 1 grows each time as well. So I'm multiplying by that quantity x plus 1. So my common ratio is negative and then the parentheses x plus 1. Don't forget your parentheses there. So what this question is asking me to do is, it says find the values of x for which the series converges. Okay, well, if a geometric series converges, we need the absolute value of the rate to be less than 1, or we need that rate to be between -1 and 1, so that way when we take the absolute value of it, it is less than 1. So most of you are going to be more comfortable in that compound inequality than in the absolute value inequality. Then, because you found those values of x that will force it to converge, you can find the sum of the series. So let me give you an example real quick, just kind of off the charts here for a second. So if I have this series right here, what are we going to think happens? So if I have an infinite sum of zeros, you can probably guess that that series will converge, right? Because the sum will be 0. Okay, well, I can find at least one value where if you put that value in for x, you have a sum of zeros. So what value would you put in for x and have a sum of zeros? Well, if x equals -1, -1 plus 1 is 0. 0 to the 1, 0 to the 2, 0 to the 3, etc. will all be 0. Whether you're adding 0 or subtracting 0 certainly isn't going to matter. You have an infinite sum of zeros. So I think there's at least one x value that I can force to make my geometric series converge. But we can find all of them. We know what that common ratio is. And I know that a geometric series will converge if that common ratio, like we said, is in between -1 and 1. So I'm going to put this common ratio in between 1 and -1, or you can use the absolute value and then remove it after. Okay, so I'm going to distribute the negative because I think that's what many of you will do. So I multiply the negative in here. And this is just the three sides. You have your left, your middle, and your right. So whatever I do to the middle, I have to do to both the left and the right side of this inequality. So for example, you can add 1, but do it to all three. So I have 0 is less than -x is less than 2. And then just be cautious because when you divide by a negative, you are switching your inequality sign. So that stays x, that stays 0, that becomes -2. And I would look at this on a number line. That might help you. So I have 0 and I have -2. And what it says, if you read it from the x, for example, it says x is greater than -2. Okay, so I'll draw that, greater than -2. And if you read it this way from the x, it says x is less than 0. And so if x is less than 0, you have an open circle on 0 and you're heading this way. So it's between -2 and 0, I converge. So I'm going to say converge if x is between -2 and 0. It's also called an interval of convergence. Okay. Then it says, now that I've found the x values, and by the way, we thought x equals -1 should be in that interval of convergence. And look, it's not only in that interval of convergence, it's actually smack dab in the middle of that interval of convergence, and that is not a coincidence. We'll talk about that as we go through the chapter and deal with power series. So -1 is, again, right smack dab in the middle of that interval, and that makes perfect sense to me. So find the sum of the series. If we're within those x values, we can find the sum of the series. And the sum of the series is your first term. Again, if I have them written out, it's much more helpful to me, over 1 minus the rate. And this is where we have to be careful with our parentheses. So I'm going to keep this negative on the numerator, but then this will become 1 plus x plus 1. So my sum is this opposite of, and I can put it just in front of my whole fraction bar like so. I just caution you because then sometimes your negative becomes your fraction bar, but that's fine. Over x plus 2. I think that we can keep them separate. If not, then keep it, with the negative in the parentheses out front. Okay, so I just did another one because I wanted to make sure you could solve for that sum. So you can certainly, get the problem, do the same thing, write out some terms, figure out what that geometric ratio is, force it to be in between -1 and 1, and then you know what your interval of convergence will be, and then you can find your sum from there. So the next thing that we're going to do is talk about what happens when a series is not geometric. So in this section, we have divergence test left, telescoping series, and harmonic series that we'll all talk about. And that will be part 2 of our sort of introduction to series, or dealing with the first parts of series here on our long last chapter. I hope you found this helpful. Thanks for watching.